this section does, again, it gets into a lot of, starting to get more into the why, we take derivatives, why this, why that. Well, again, the first derivative tells us a lot about the original function. The second derivative tells us a lot about the original function. And so you know a lot about the original function without actually graphing it on your calculator, by just sketching it. And you can tell a lot of information, but you need to know a lot of derivative stuff in order to do it. We got a quick typo change too. For some reason, Mr. Remus can't. I don't know what I was thinking here. But what we're going to do is connect the derivative graph and the second derivative graph with the original function. That's the title of 4.3. From the last section, we can figure out when a function is increasing, decreasing, and where the extremum are located by examining f. When do I know an original function is increasing? Amina? How can I tell when original function is increasing by looking at the derivative?
Positive.
Positive. Joanna, how do I know the original function is decreasing? If it's negative. How do I check for possible min-max points? Wayman, where do I check? Or? Yes. And if it's on a closed interval, where else do I have to check? Eleanor. If it's on a closed interval. At the endpoints. Cool. Alright. So I got some function here, x squared minus 4x plus 3. And I want to know, let's say in this case, where it's increasing, decreasing, and any min-max points. So I take the derivative, I get 2x minus 4. I set it equal to 0. And I get x equals 2. And then what I don't do is when I start making my little table, I put 3's all over here, because that would be weird. So I'll go ahead and just change all these back to 2. I have no idea why I did that. Here's this interval. It doesn't make any sense at all. Alright, there we go. Because that wouldn't make any sense. Just to really keep you on your toes. So because there is 3 and 3, the maximum at 2. Okay. So change all those random bizarro 3's. I don't know. Same thing with original. I spelled it right on this one too. I sound pretty excited. Okay, so I have my critical point. I have when the derivative equals 0. And it's never undefined, so that's the only critical point at 2. So at an x value of 2, the derivative is 0. The only time a derivative can change sign from positive or negative is for either to cross the 0 or when it's undefined. So the only time this thing can change from positive to negative is here. So in my sign chart, I only have to check to the left and to the right of this 2. Okay, Anna? So I look at my derivative, which is here, and I plug in a number less than 2, like 0. And this thing becomes negative. Again, I don't care about the value, I just care about positive or negative. Alright, Brandon? I plug in 0, I get negative 4, so the derivative is negative. I plug in 14.8, and I get a positive value. Yes? Okay? So then I make a little chart. My derivative is negative here and positive here, which means the original function had to have been decreasing and then increasing. And looking at that, that means that that little bugger 2 has to be a min. Amina.
How do you know there's not like another term? Yeah.
Because, what a wonderful question that I will answer now.
Okay.
The only time you can turn is, the only time the derivative can change from positive to negative, like, so if you have the derivative, you're looking at the derivative. The only time it can go from positive to negative is to go through 0. Or if it's undefined. And so here's my derivative function. This thing only equals 0 once at 2. Which means that's the only time it can change from increasing to decreasing. Yes?
Okay, so then if the derivative function was like a quadratic or something and there were 2
This
possible values.
A cubic, you mean?
I mean, if the derivative was a quadratic.
Okay, yes.
Then you wouldn't be able to do that.
We can. It'll just take a little more algebraic work, which we'll do in another example. Yeah. Yeah, it could be as many as you want. Like this is just, obviously I start with like the simplest one. If the derivatives align, and then it's like, hey, increasing to decreasing. But yeah, that last little w is a quartic, so it's an x to the 4. So there's a whole bunch of mess happening. And we'll get to that. Good call. But again, that's what's so neat about this. Just exactly as it is, how do I know it doesn't shoot back up again? And I know for sure it doesn't shoot back up again, Because the only time it crosses 0 is at 2. So if that's the only time, that's the only time it can switch from positive to negative. Does that make sense, Chris? It cannot switch. Because it can't, I don't care how much positive or negative, here's your function, and it never crosses, it can be snuggy or whatever, it's just not going to cross, you know? Because in order to get up here, you got to cross through the 0. And I already solved for all the zeros. Nathaniel, how are we feeling with that? Okay, good. So, because the derivative is negative to the left of 2 and positive to the right of 2, the function has a minimum of 2. And again, what you can do is just this little baby sketch. We'll show that to you. Does that make sense, Johnny? Yeah, it just goes to, so it's just that. Okay, it's got to be a min. All right? So again, not only have I located where it is, now I actually know that it is a min. So I know like one extra level beyond extreme value theorem. You know what I'm saying? Using this little idea. Okay? So what we're going to call this is the first derivative test. That's kind of a big one. It comes up in various different ways. But the first derivative test tells me if you have a derivative that's equal to 0 or undefined, and then you check to the left and to the right of it, you can guarantee yourself or let yourself know that it's a min or a max. Let me get rid of all these 2. So for example, this top example, you have a derivative equal to 0 at some point c. The function derivative is positive and then negative. And you guys get used to this sort of notation. See f prime greater than 0? That just means derivative positive, which means the original function increasing. Does that make sense, Anya? So here's just a real quick way to say derivative positive. F prime greater than 0. F prime less than 0. So the derivative goes from increasing to decreasing. When that happens, when the derivative changes sign from positive to negative at c, then f is a local max. Not global, just a local. Yeah, just guarantee yourself no idea about the highest or lowest, but you just know this is a candidate for one of the maximums, you know. It's definitely a local. But again, it doesn't tell me anything about the overall global. But, you know, it gets me started. If the derivative changes sign from negative to positive at c, then f is a local min. Again, changes sign. Here's the derivative is negative. F prime less than 0. Or the derivative is negative. F prime equal to 0. F prime greater than 0. The derivative changes sign from negative to positive. You got yourself a min. Now, what's also neat about that, Rafi, again, it's either if the derivative equals 0 or undefined. You see I do this silly little cusp up here? You know, derivative is positive and then negative. Even though the derivative doesn't exist there, that's still a max. And don't forget that, because that's the one we'll forget. We'll be fine with derivative equal to 0, Michelle. Always forget the undefined one. But you can still, because you still have a value there. You know what I'm saying? You don't have a derivative value there, but you definitely have a function value, just kind of a little cuspy guy. And then same thing with like, you know, here's an example of decreasing, undefined, increasing, like absolute value. And then sure, yeah, this is still a minimum. Again, at the critical point, to the left and to the right of the critical point, you go from decreasing to increasing. Where a critical point is both where the derivative equals 0 and undefined. Okay, so check both. And then, you know, you also have endpoints. So you have a left endpoint here. Scoot over a little bit. That's it. That's right here. It's like right here. There we go. So if you have an endpoint and you shoot off decreasing, that's a max. Do you know what I'm saying? Because you have some point, you're on the left, and you shoot off going down, well, that had to be the highest point. If you have a point and you're shooting up, like now the function is increasing, derivative is positive, well, it had to have been a min, because now you're just going higher and higher. So that's from the left. And then from the right, it's just kind of the flip of that. If you're coming up, and you're decreasing coming up to the point, well, that's going to make it a min. If you're coming up to the point and the derivative is positive up to it, well, that has to make it a max.